So I thought it only appropriate that I should wear it to introduce him. And he's going to talk an exciting topic, homotopy. Link, is it homotopy or homotopy? Where does one put
Well, if you're American, it's homotopy, but...
Homotopy, yeah. Higher helicity.
Okay, so thanks very much for asking me to speak and for inviting me to the program, which is really, I've had a blast so far, and hopefully that will continue. So let me just mention collaborators. So the original group was this group sort of in the middle here, and then it expanded in a later paper to include Hagai Nucci, and then Rafal and I sort of formed a splinter group with Fred Cohen. So it's sort of a complicated amalgam of different people. But here's the basic motivation, is to find topological invariants of vector fields which provide lower bounds on the field energy. So the story I want to tell is a story that's sort of inspired by this physical problem, and sort of leads into interesting problems in geometric topology, but then also sort of algebraic topology. And then the hope is that eventually we can bring it back to the physics. At this stage, everything I'm going to say is really math, not physics, but the hope is that we can sort of translate back into physics eventually. So of course, the model for such a thing is the helicity. So if I have a vector field, just let me say supported on a compact domain, then the helicity of the vector field is given by this integral. So notice that I'm integrating over domain cross domain. So this is really like a 6-dimensional integral. Well, what is it good for? Well, it gives this lower bound on the field energy. So let me actually do this starting from the bottom. So I guess the reference I have in mind is Arnold, but actually the ideas go back before Arnold, Vulture, and in fact Keith Moffat and other people, that if your helicity is non-zero, then that provides a lower bound on the field energy. The energy, and this lambda here is like the eigenvalue of or it's sort of the largest eigenvalue of the Biot-Savart operator is sort of the way to think about it. So if the helicity is not zero, the energy is sort of bounded away from zero. Yes, I should have said that, yes, the L2 energy, right. Okay, well, in and of itself, that doesn't really tell you anything because you don't care about vector fields as sort of static objects. You want to think about them, evolving under, say, ideal magnetohydrodynamics or the Euler equations or various other things. So you want to know that this thing can't go to zero under such an evolution. So that's what the top theorem tells you, is that the helicity is invariant under, pushing this field around by volume-preserving diffeomorphisms, just sort of treating it as a frozen-in field and just moving around by these volumorphisms. And so if you're interested in ideal magnetohydrodynamics, for example, well, the evolution according to ideal magnetohydrodynamics is by volume-preserving diffeomorphisms, homotopic to the identity. Of course, in real life, you can have reconnection and topology breaking, but in the ideal setting, this provides a lower bound for the energy under such evolution. So that's why one should probably care about helicity. And then, of course, the problem is that helicity is not always non-zero. It can be zero even in situations where the energy really shouldn't be able to be sort of relaxed away to zero. So the dream is to build sort of a hierarchy of helicities. So I have the first helicity, but if that's zero, I have a second order helicity that kicks in and provides me a lower bound on the energy. If the first two are both zero, then you want a third order thing that kicks in and so on up the line. So this is from Arnold and Kessen's book. Well, if you want to do that, how can you hope to define such a higher order helicity? Well, it seems like, well, where does helicity come from? Can you sort of do the same thing that you did to get helicity in order to get these higher helicities? So here's the helicity integral again. And then the way that I really want to think about it is by analogy to the Gauss linking integral. This was not how Vulture originally defined helicity, but this is an equivalent definition. And the analogy, just looking at the formulas, is sort of obvious. So I have a two-component link parameterized by x and y. Then the Gauss linking integral says, well, the linking number between the two components is given by this integral. And if you just replace dx ds and dy dt by instances of v, they're the same equation, right? More or less. And let me just show the picture here. So this dx ds cross dy dt dotted with whatever, so it's a triple product of the tangent vector to the one curve, tangent vector to the other curve, and then some scaled version of the vector pointing from one to the other. So this is just the volume of the box spanned by those three vectors. And again, if I put these two formulas next to each other like this, then this statement is fairly transparent that the interpretation of the invariant meaning helicity in terms of conservation of knottedness of magnetic lines of force is immediate. So any guesses who wrote this? You have a guess, rather.
I was guessing Keith wrote.
Indeed.
I thought I did.
Yeah, so Keith was, I think, probably the first person to really notice this. And then Arnold proved a very rigorous theorem about the helicity of a vector field is the average asymptotic linking number of its orbits in some appropriate sense. So helicity is really some sort of an asymptotic linking number. And just briefly, this interpretation gives you a good sense of why you get a lower bound on the energy. So if I imagine that I have a vector field with closed orbits, so just think about within these tubes, I just have closed orbits going around longitudinally. Well, if I want to decrease the energy, I need to shorten those tubes, right? I need to, I want to bring the velocity down, so I have to shorten the tubes. But if I want to do that in a volume-preserving way, I have to fatten the tubes up. Well, of course, if you're fattening both of these tubes, they're linked to each other. So you can't shorten forever. Eventually, you get caught up on the other guy. So you can't make the energy go to zero because you just can't keep fattening these tubes forever when they're linked. OK, and then one other comment I want to make about the linking integral is that, well, the analogy with helicity tells you that it's some sort of physical quantity. And in fact, you can sort of interpret it in terms of Ampere's law or whatever. But so the integrand is really physics is happening in there in some sense. And this integrand, if you think about it, well, again, it's the volume of this box. Well, if you move your link around by some isometry, you're not changing the volume of the box, right? You're just moving the box around, but it has the same volume. So this integrand is actually isometry invariant. And that's what I want to call sort of a geometric naturality condition. That not only is this integral computing a topological invariant, the linking number, but the integrand itself is invariant under isometries. So then that's really the goal, is to find generalized Gauss linking integrals that compute higher order linking invariants and are geometrically natural in that sense. And of course, for physics, I mean, that's the very least you could possibly expect, right? Because your coordinates, which coordinates you pick, can't possibly matter. So the integrand sort of had better be at least isometry invariant, if not more. And then the hope is that you can extend from links to vector fields and get higher helicities. But I would emphasize that that's still speculative. I guess for people that don't care about vector fields so much, I would also point out that the Gauss linking integral is, sort of what gives you things like link equals twist plus writhe and various other things. So if you have geometric integrals for higher order linking invariants, one could hope for other higher order analogs of those things as well.
Can I ask a question?
Uh-huh.
For Gauss linking integral, it's the linking of the field of tangent vectors.
Mm-hmm.
That's correct. But they, when you have volume preserving transformation, then they evolve in a the tangent vectors remain unit vectors. But if you have a magnetic field, the magnitude of the vector does change.
Right, so the integrand is not going to be invariant under like volumorphisms.
Right, but you integrate it up.
But when you integrate it up, so this quantity is going to be invariant under volumorphisms, but the stuff you're integrating is not going to be.
But you have the same process. At once you have a field of tangent vectors, and then the same thing exactly, but the magnetic field. The field in both cases is different. So,
but the theorem of Arnold and others is that you get the same number.
that doesn't affect the number, but it affects the energy.
Sure, yeah, for sure. But the point is the helicity gives you a bound on the energy, so the energy can only go down so far under that process.
There's a flux constraint. That was sort of implicit in this. The flux constraint is not satisfied.
I thought you were
Because you increase with the tangent vectors, the vector stays the same, but the cross section increases, so the flux grows.
Right, but I
The
think
relaxation process.
I think
The
if you,
flux is conserved.
in your argument,
Not on the tangent vector, because the vector is the same where the cross section increases. Well, if you do this to the field decreases when the cross section increases.
But this isn't the unit tangent vector, it's like, if your field is slowing down, the tangent vector
have
has
to
to be shorter.
complement this with some evolution equation. Right? Maybe not.
I don't
Never mind.
well, it's also the linking, not the helicity.
Right.
I mean, yeah, so this integral is just the linking. Okay. Right. So, so the idea is to build higher order analogs of the Gauss linking integral, and then so you have to ask yourself, well, where did that thing come from? How it didn't just come out of nowhere, it came from somewhere. So where is that somewhere? Well, sort of the standard answer is that, if you have a two-component link in R3, you can define a Gauss map, which is just, the unit vector pointing from a point on one component to a point on the other component. It's just written out like this. So that gives you a map from the 2 torus to the 2 sphere. And then, the theorem of Gauss, appropriated or translated to modern language, says that the degree of that map from the 2 torus to the 2 sphere is equal to the linking number of the link L. Right. So, of course, it's not so clear how to generalize this, right? So the 2 torus is just the product of the parameter circles. So it's clear enough that if I have n components, I should have n parameter circles. So this should be like an n-dimensional torus on the left. But where'd the S2 come from, right? I mean, we're still living in R3, so it's not like the n-1 sphere or anything. So where does the S2 come from? So I claim that the way to think about it is, I'm a slide ahead of myself here. So backing up a step. So the degree is equal to the linking number, and then if you just compute the degree in the usual way, you take a volume or an area form, you pull it back, you integrate over the domain, that gives you the degree of the map. And if you just expand this out using that G up there and the standard area form on the 2 sphere, then you're actually going to get the Gauss linking integral, the exact formula that I wrote down before. So that's, I claim, where the Gauss linking integral comes from. But then the real question is, well, how to generalize this map? So I want to go up a step in abstraction. I want to say, well, this map is really not a map from the 2 torus to the 2 sphere. It's a map from the 2 torus to the configuration space of 2 distinct points in R3. So, right, this is a submanifold of the product, R3 cross R3, where I'm not allowing the points to come together. They have to remain distinct forever. Now, that space, deformation retracts to S2. I have 2 distinct points. I just translate to one's at the origin and then scale to the other one's a unit length away. So that's a deformation retraction to S2. Just realized exactly by this map here. XY goes to X minus Y over the norm. Now, of course, the composition of these two maps, I have the map from the product of parameter circles just to the parameterization of the link, and then combine that with this homotopy equivalence. Well, that is the Gauss map, and then Gauss's theorem says that the unique homotopy invariant of the map from the two torus to the configuration space is equal to the unique link homotopy invariant of the two-component link. Okay, so in other words, it's saying I have some linking invariant, the linking number. I can interpret it as a homotopy invariant. In this case, it's a degree, but in general, it could be something more complicated. And so I've translated linking invariance to homotopy invariance. And that's sort of the key idea here. Is I want to, so I'll say what link homotopy means in a second, but just think I have link invariance of links. I want to translate those to be homotopy invariants of maps. And then once I have homotopy invariants of maps, you can hope to write down integral formulas for them. So a link homotopy just means the following. I have some number of components. Now, each component is allowed to pass through itself. That's OK. So the blue can pass through the blue. The red can pass through the red. But red and blue have to stay away from each other. So blue can't pass through red, but blue can pass through blue. So I can change this crossing by just passing the understrand through to this crossing. Well, in so doing, I've turned the Whitehead link into a trivial link. So this is a much weaker notion than isotopy of links, because, of course, the Whitehead link is a very famous non-trivial link, but I've turned it into a trivial one by one of these link homotopy moves. And okay, right. So in general, I want to compute, or I want to consider parameterized incomponent links sitting in R3. So I want to think of the link as really being a collection of maps from the circle to R3 with disjoint images. So I don't want the red and the blue to ever intersect. They should always stay away from each other. And then I'm going to let LM, just standing for link map, LM of n to be the set of link homotopy classes of incomponent links in R3. So they're links up to this move where I'm allowed to pass a component through itself. And then I get a very natural map to the configuration space. So I have these circles, which are just the parameterizing circles. So for each one, I have a map, Li into R3. So for n of them, I have maps in principle into R3 to the n. But again, they have disjoint images, so points have to stay away from each other. So in fact, I'm living in this configuration space, which is just the set of all n tuples in R3 where no two points are allowed to be the same. So this is sort of a very natural evaluation map that one can associate to any link. And then link homotopies of the link induce homotopies of the map. That's, this is, you have to think about it for a few minutes, sort of quietly, but it's fairly easy to convince yourself that this is true. So what does that tell you? It tells you get an induced map, right, from link homotopy classes of links to homotopy classes of maps from the n torus to the configuration space. So I have a link, I get this induced map from the n torus to the configuration space. And if I do a link homotopy over here, I stay in the same class. And the point is that sentence up there implies that I stay in the same class over here. So this map is well defined.
That's a one-directional statement. Homotopies of GL don't necessarily.
That's the key question. In fact, that's the key question. Is this map injective, right? So what I'm doing is I'm translating links to maps. And the question is, do you lose information under that translation, right? Is this, is this a lossy sort of encoding scheme? So if you can do a homotopy over here that didn't come from a link homotopy over here, then you're sort of in trouble, right? You've lost information by going from links to maps. But the question is, well, do you lose information? Can you translate from one to the other without losing anything. So that's just translated into fancier language, exactly Shorka's conjecture. This map from links to homotopy classes of maps is injective for all n bigger than or equal to 2. In other words, translating from links to maps is, not a lossy translation. So then if Shorka's conjecture is true, you can just translate linking invariance into homotopy invariance. And then once you have homotopy invariance in your hands, at least the Gauss integral sort of tells you, well, you have a chance of writing down nice integral formulas for those homotopy invariants.
You should know this, but configuration space, like what are its Betty numbers? I mean, how complicated is it?
In principle, it's fairly complicated. It's like an iterated bundle of wedges of spheres. So like it has the rational homotopy type of a wedge of 2 spheres, like a lot of them. So it's very complicated.
He claims that it's the cohomology of some flag.
All right, so it's complicated.
It's complicated, but in some ways well understood. So the nice thing is that very nice presentations, or you can write down like generators of homotopy groups in a fairly nice way. So it's nice in that sense that the algebra is complicated, but you have sort of the building blocks are fairly well understood. Okay. Uh-oh. What happened there? Okay, so that was Shorka's conjecture, but of course anybody can make conjectures. Why should you possibly expect it to be true? Well, the n equals 2 case is Gauss, right? He's saying you have links over here, you have maps over here, the linking number is the degree of the map, those are the only invariants. On both sides, those are complete invariants. So in fact, it's not only injective, it's bijective. You're immediately going to lose bijectivity as n gets bigger, but the hope is that injectivity will stay. More evidence is going to be talking about the set of homotopy Brownian links. So what are these? These just mean that if you delete any component, the whole thing falls apart. So like the Borromean rings, if I remove this blue component, the green and the red just fall apart. And likewise, if I remove the red or the green, what's left falls apart. So you can remove any single component, and the rest of the link just falls apart. So that's what I mean by a Brownian link. And then Shorka proved that his map is injective when you restrict to the Brownian links. So at least on this class of links, it's injective. Okay, so more evidence. So let's now focus on the case n equals 3. So 3 component links were classified up to link homotopy in Milner's undergraduate thesis. So there's 4 invariants. So you have the 3 linking numbers. So red with blue, blue with green, and green with red. So that gives you these 3 integers, which I'll call P, Q, and R. And then you have a 4th invariant, which I'm just going to call mu, but the fancy name is mu bar 1, 2, 3 because it's part of some hierarchy of invariants. And this thing is only an integer modulo the GCD of the pairwise linking numbers. Now, when the pairwise linking numbers are all 0, like for the Borromean rings, then this is actually an integer. But in general, it's only an integer modulo this GCD. So the actual definition involves a lot of algebra. It's straightforward, but a little bit complicated. But it can also be so this was Blake Malor and Paul Melvin show that you can interpret it geometrically in terms of sort of counting intersections of components with Seifert surfaces for the other components, and adding on a count of the number of triple point intersections between the Seifert surfaces. So in this picture, you see that triple point right in the middle where the 3 Seifert surfaces intersect, and that's that's adding a +1 or a -1, depending on signs, to the Milnor invariant for the Borromean rings. And it turns out that if you go through looking at the components piercing Seifert surfaces, that all contributes 0. So just that triple intersection point gives you the 1 for the Borromean rings.
Is that independent of which Seifert surfaces you choose?
Yes. So that's the key part of their proof, is that it doesn't matter what Seifert surfaces you pick. Or really what they did is they said, you have any Seifert surfaces, you can do a bunch of finger moves to get into sort of a standard form and then apply a previously known theorem.
I was thinking, I mean, take the green Seifert surface there. If instead of that disk, I ballooned it out so it was right outside the other two, you don't seem to have a triple point at all. But,
right, but then this other stuff is going to come into play.
I see.
And, well, no, I think you probably will still have a triple point.
Maybe you have to extend the other disks as well. I don't know.
Yeah, well, okay, yeah, this is going to come into play because you balloon the green out, but then now you have an intersection of the blue with the green. So then what happens is you follow the blue around, you see like red, green,
I see, yes.
and that's going to, it turns out, contribute 1 in this other count that I'm not really telling you about.
Okay.
Yeah. It's also
So
complicated.
part of the proof. Yeah.
Yeah.
Another comment is that Seifert surfaces play a role in some sense in the relation back to helicity by doing a flux integral. And similarly, this Miller-Melvin thing at least gives some hope that you get some kind of energy back in terms of fluxes in the Seifert surfaces. Triple linking.
Sure.
Wishful thinking.
Yeah, right. Yeah. Yes. So, okay. So I have 3 component links. I want to write down, well, first off, I want to understand, is this Kashorka map injective for n equals 3? Well, so it's going to turn out that working in S3 is going to be easier to start off with. So I'm going to have a 3-component link in S3. Then again, I have a natural evaluation map now to the configuration space of 3 points in S3. And the reason it's easier to work in S3 is because that space is homotopy equivalent to S3 cross S2. And here's the picture. So I have 3 points, x, y, z in the 3-sphere. Then I can stereographically project from z to the perpendicular 3-plane. So that gives me a blue point and a red point in this 3-dimensional slice of R4. Well, so now I have 2 points in R3, basically. Again, I can translate to ones at the origin, scale to the other ones a unit length away. And then I'm going to inverse stereographically project back to the sphere. Well, what happened? Well, that point that translated to the origin ends up at -z. And the point that I scaled to be unit length away is sitting on this equatorial 2-sphere that's halfway between the z and -c. So now I have a point on this 2-sphere, and then z and -z are encapsulating the same information. So this is a 2-sphere bundle over S3. Of course, all such things are trivial, so it's S3 cross S2. And then the other point to make is that the S3 factor is just recording where z was, which can't possibly matter because you can move z around by isometries, if you like. So really, all of the interesting information is, in fact, contained in this S2 factor. So I'm just going to project to the S2. And when I do that, I have this composition from the 3 torus to the 2-sphere. So given a link, a 3-component link, I get a map from the 3 torus to the 2-sphere. So here's a picture of the 3 torus. So what's the 3 torus? Well, I can just take the integer lattice in R3 and mod out R3 mod that lattice. So a fundamental domain just looks like a cube. And then all I have to do is I have to identify the left face and the right face, the top face and the bottom face, the front face and the back face. So I have a map from that space to the 2-sphere. And such maps were classified by Pontryagin in the late 30s and early 40s. And again, there's 4 invariants. There's, since top and bottom are the same, left and right, front and back, there's really only 3 faces here. But each of those faces is a 2 torus. So if I restrict to a face, I have a map from the 2 torus to the 2 sphere. Such a map has an associated degree. And that degree has to be a homotopy invariant of the map. So I have these 3 degrees of the restrictions to the 2-dimensional subtori. And then I have a secondary invariant, which is sort of analogous to a Hopf invariant. And this turns out to be defined modulo twice the GCD of the degrees. So remember, Milnor classification of 3-component links, I had the pairwise linking numbers and the triple linking number, which was defined modulo the GCD of the pairwise linking numbers. Here I have 3 degrees. And of course, we know from Gauss that degrees and linking numbers should be analogous. And then I have this higher invariant, which is defined modulo twice the GCD. So you can't stare at that for too long before you make the obvious conjecture that the degrees are equal to the pairwise linking numbers. And the Pontryagin or Hopf invariant of the map is equal to twice the Milnor invariant of the link. And so that's this theorem that we proved. Exactly that you don't lose any information by translating from links to maps in this way. And of course, this was a map from the 3 torus to the 2 sphere, but the whole point was that it captures all of the interesting homotopy information of the map from the 3 torus to the configuration space. So this, what you could call like a spherical Koshorka map, is injective. Okay, so let me try to tell you the basic ingredient of the proof at least. So the basic ingredient is to understand what happens when you apply what's called a delta move. So the delta move, it looks, if you aren't looking too carefully, it looks like a Reidemeister 3 move. It's like a sort of a fake Reidemeister 3 move. And it turns out that it doesn't change the pairwise linking numbers. And there's this great theorem of Murakami and Nakanishi saying that if you have 2 links with all the same pairwise linking numbers, you can get from one to the other just by doing a sequence of delta moves. So then here's the strategy of the proof, right? We're going to, for any given list of linking numbers, we're going to say, okay, here's our standard link with those linking numbers, and show that the theorem holds for that link. But then for any other link, I can get there by a sequence of delta moves. So then I just have to understand how the delta moves change my 2 invariants. So it's fairly straightforward to see that the delta move increases mu by 1. So this is before the delta move. Here's my Seifert surfaces. After the delta move, I picked up this triple point. All the other intersections between the blue component and the green surface are just canceling pairs, so they don't contribute anything. So this gives me a +1, this triple point. Of course, there's a hard part, which I will not bore you with, but basically we developed this sort of topological calculus for computing the Pontryagin invariant of a map associated to a 3-component link, and then eventually showed that when you do a delta move to the link, it increases the Pontryagin invariant of the map by 2. So you increase mu by 1, you increase nu by 2, and that's exactly what you should expect in this picture, because nu is supposed to be twice mu. Okay. Well, fine. But that theorem was about links in S3. If you have interest in eventually applying to vector fields, you should really probably be more interested in links in R3. But it's actually, at least the homotopy story is very straightforward for such things. So if I have a link in R3, again, I have this evaluation map to the configuration space of points in R3. Of course, I can embed that in the configuration space of points at S3 just by introducing the point at infinity in each coordinate. But then I have this projection down to S2. So for a link in R3, again, I get a map from the 3 torus to the 2 sphere. And the homotopy invariants of that map give me the interesting homotopy invariants of the map of the evaluation map. So again, this Koshorka map is going to be injective. And this should be a 3. So for 3-component links, if you care about linking and link homotopy invariance, you can translate over to maps and talk about homotopy invariance, and you haven't lost any information. That's all that this is saying. Okay. But if you want to cook up an integral, you have to dive in a little bit more deeply. So, let me now build up to writing down an integral formula for mu. So that's going to be from interpreting this Pontryagin invariant as sort of a Hopf invariant, and then writing down the Whitehead integral for the Hopf invariant. So I have a map from the 3 torus to the 2 sphere. If the pairwise linking numbers are all 0, so if the restriction to the faces are all homotopically trivial, well, then I might as well actually do that homotopy and make the maps constant maps on each face. So what have I done? I've just squished the entire 2 skeleton to a point. So now I've turned the cube into a 3 sphere, and now I have a map from the 3 sphere to the 2 sphere. Well, maps from the 3 sphere to the 2 sphere very much do have Hopf invariants, and Whitehead told us how to compute them, or one way to compute them, right? So I have a smooth map from the 3 sphere to the 2 sphere. I have the normalized sort of round area form on S2. Then if I pull that form back, I have a closed 2 form on the 3 sphere. Of course, the 3 sphere has no second degree cohomology, so a closed form is exact. So it has a primitive. So I'm just going to use this notation to indicate some primitive of the form. And part of Whitehead's theorem is that it doesn't matter which primitive you take, it's all the same thing. So the Hopf invariant of the map is just the integral of, the 1 form primitive of this 2 form wedge the 2 form.
So that's somehow a dual version of Keith's question, I guess, about picking Seifert surfaces.
Yeah, sure. So those of you who don't like primitives of forms, this is, just think of, I have a smooth map, right? So now I'll take the inverse image of a regular value, take the inverse image of 2 regular values, compute their linking number. That's what this is doing.
Also the vector potential, right?
Yeah, well, exactly, right. If you interpret this as a vector field, this is just a vector potential. So this is also the helicity of some associated vector field. Okay. So now I'm going to do the same thing for maps from the 3 torus to the 2 sphere, where the pairwise linking numbers are all 0. So the degree on each face is 0. So if you like thinking in terms of vector fields, the flux through each of these faces is 0. So there is a vector potential. So then the Pontryagin invariant of the map is this essentially same integral. You take the vector potential dotted with the vector field, and that gives you the Pontryagin invariant. And then the previous theorem told you that the mu invariant is half the Pontryagin invariant, so the mu invariant is half of this integral. Okay, so now here's where you object and say, yeah, but you made a hell of a lot of choices, right? You're picking any old primitive. Your map was like, you have an evaluation map and an inverse stereographic projection and then a projection, and that can't possibly be isometry invariant in any reasonable sense, and I agree with you. So I need a much nicer map from the 3 torus to the 2 sphere if I want to actually get an integral formula that has this geometric naturality condition that I said at the beginning. So here's the nicer map. So it's going to be a composition of the evaluation map with this map. So this map is a map from the configuration space of 3 points in R3 to just R3 minus the origin. Of course, eventually I'm going to scale so that it's on S2. So it's very important that it never hits 0. So what's the map? Well, so I have my points x, y, z. So they're distinct, so they define a triangle. Now this triangle could well be, sort of a degenerate triangle that sits on a line. Like these 3 points could lie on a line. But generically, you're going to get a triangle, and then I have sides A, B, C, and then the opposite angles, alpha, beta, gamma. And then I'm going to define this map just to be A over the length of A plus B over the length of B plus C over the length of C. Okay, well, so if I focus on C over the length of C, well, what's C? C is just y minus x. So y minus x over the norm of y minus x, that's basically just the Gauss map. So this is like a symmetrized Gauss map. Of course, you can't just have that. So you also have this other term. So I have sine alpha plus sine beta plus sine gamma. And you should think of this as being like a dimensionless area, right? The area of the triangle is like half the cross product, half the norm of the cross product of B and C. So the norm of the cross product is just norm B, norm C, sine alpha. So if I take norm cross product divided by norm B, norm C, I get sine alpha. So this is somehow analogous to the area. And again, symmetrized over the three possible choices. So my ingredients are this evaluation map and then this sort of triangle map. So I'm going to define my generalized Gauss map from the 3 torus to the 2 sphere as just the composition of evaluation and then F and then normalized so it lies on the 2 sphere. And you can write this out sort of very explicitly in coordinates if you like. And then the theorem you have to prove is that that map is homotopic to the other map, and therefore the mu invariant of the link is half the Pontryagin invariant to the other map, while the other map is homotopic to this map, so they have the same Pontryagin invariant, so then I can compute in this way. Okay. So that's going to take care of the map. Now I have this very nice symmetric geometric map. But of course, I also need to do a good job of picking my primitive. I should pick some sort of geometrically natural primitive for the form. And I mean, the obvious choice is the primitive with least energy, or smallest L2 norm, right? If you think in terms of vector fields, this is basically just taking the Biot-Savart operator applied to the vector field, or if I write it in terms of forms, I can think about convolving my form with the fundamental solution of the Laplacian, and then just hitting it with the co-derivative. So this is a 2 form, this turns it into a 1 form, and then d of that form is equal to omega L. And this is guaranteed to be the primitive of omega L that has smallest L2 norm. Okay, so let me do a brief digression on this fundamental solution so you can write it out in terms of a Fourier series in this way. So I'm summing over all triples of integers that are not all 0, and then this is just 3-dimensional Fourier series. So the 2-dimensional analog looks like this when you graph it. So you have singularities at the lattice points, and that's also true for the 3-dimensional one. But then it looks sort of like a Morse function, right? You have sort of like this infinite max, but then you have saddle points in the middle of the edges and a min in the middle of the face. And it's away from the singularity, it's a nice C infinity function. So if you put all of that stuff together, the triple linking number of the link is half of this integral. So I have this form that I got from pulling back the area form on the 2 sphere. I have this very natural primitive for it. If I integrate their wedge product, I get twice the triple linking number. And then it's not so obvious from the way that I've written it out, but in fact, this integrand is going to be geometric in the sense that it's invariant under orientation-preserving isometries of R3. So if I move my link around, I don't actually change the integrand at all. And of course, we have a Fourier series for the fundamental solution. Convolutions play extremely nicely with Fourier series, so I can write out mu just as essentially a Fourier series, where this A and B are just the real and imaginary parts of the Fourier coefficients for omega.
An interpretation of a single n as like a wave number or something. I mean, so this is a sum of, it's a superposition of something. Does each
Well, so you should think about the cube is sort of like the fundamental domain in R3. And I'm really having to sum, so in principle, you want to take the potential in R3, but you have to sum over all of the fundamental domains. You You have to average over those guys with appropriate scaling given how far away they are. So it's like a superposition of all the possible fundamental domains. I don't know if that answered your question.
No, it's fine. Yeah, that's fine. That makes one sense. So there is some kind of fundamental solution, but you're just kind of averaging it.
Right. I mean, you're basically taking the R3 fundamental solution and just averaging it over all the fundamental domains.
So I should think of n as a deck transformation.
Yeah, sure. Sure. Okay, so this then was the goal, was to, well, the first part of the goal is get a nice geometric integral formula for the triple linking number. Now, what I don't know how to do at this point is to translate that into a higher helicity. This is certainly something that Rafal has thought a lot about, and of course, I mean, I should have said a long time ago that, I mean, this idea of turning higher linking invariants into higher helicities is a very old, idea. It goes back at least to Monastyrsky and Ratak, if not further. But I think this idea of sort of translating linking invariants to homotopy invariants is in some ways new. But anyway, so we get this integral formula for the triple linking number, and then it's very much an open question whether you can actually translate that into a vector field invariant. My suspicion is that actually the answer is no, for sort of dumb reasons relating to the fact that you have three, well, let me just say, relating to symmetries of the triple linking number, there's sort of good reasons to think that you can't get a vector field invariant out of this. In general, I mean, certainly if your vector field's constrained to flux tubes, or in general, sort of like you have invariant domains that are handle bodies, then you're in business. But I'm dubious whether this can really be, in full generality, a vector field invariant. But that's still pretty open. And I just do this slide to point out that this Fourier series actually allows you to do numerical computations if you want. So this is a parameterization of the Borromean rings. And if you just compute Fourier coefficients by just subdividing each of these parameter domains into 256 subintervals, take your n's from -64 to 64, throw it all into MATLAB, wait a few minutes, then the number that it spits out is 0.9999997. And the answer is supposed to be -1, so that's pretty good. So, of course, in real life, links are not so nice as this link, but at least in this case, it's actually doable by computer. Okay, so the moral of this whole story is that, well, at least in the n equals 2 and n equals 3 case, interpreting link homotopy invariance of links as homotopy invariance of maps gives you these nice geometric linking integrals. And let me just remind you that Koszork's conjecture was that you can always translate linking invariants to homotopy invariants. So of course you want to go up. What about n equals 4 or 5 or n? So Koszorka, let me remind you again, Koszorka proved that this kappa map is injective when you restrict to Brownian links. So that was Koszorka. But Fred and Rafal and I said, well, you can understand the image of this map a little bit better than just saying that it's injective. In fact, the image of the Brownian links inside this set of homotopy classes is in fact a group. So one key point is that the thing on the right is just a set. It has no algebraic structure in principle. But you can see a copy of the nth homotopy group of the configuration space sitting inside of there. And in fact, the image of the Brownian links is inside that homotopy group. Okay. Well, this is a higher homotopy group, so it's abelian. And the image of the Brownian links is just a free rank n-2 factorial module. And it's generated by things that are well understood. In a minute, I'll show a picture of what I mean by a Ptolemaic epicycle. But let me just say that these are fairly well understood, and these iterated Samuelson products are things that at least homotopy theorists are fairly comfortable with. And moreover, So I have a link, I turn it into a map. Well, that map lives in this group that has a nice module structure, so I can write it out in terms of the basis for that module. And the coefficients of the basis elements in that expansion of the map are exactly the Milnor invariants of the link. So not only do you not lose any information by passing to maps, but in fact you can see all of the Milnor invariants of the link in terms of homotopy information about the map that's reasonably explicit. Now this is still a far cry from writing down a nice geometric integral formula, but in principle there are like Chen's iterated integrals to compute these things, and one could hope to maybe make those geometric as opposed to just topological. So what do I mean by a Ptolemaic epicycle? Well, this is the basic sort of map. So I have maps of the two-sphere into the configuration space. And basically what you do is you just pick two coordinates, the ith and the jth. You make one the center. And then the other one, as C moves around S2, this just moves around a sphere centered at this point. So, just imagine I have the sun sitting there, and then the Earth is sort of orbiting around it. Now this is an S2 orbit, not an S1 orbit, but it's the same idea. Now, of course, there's more going on, right? Because then I can have another map where this point is the center of some other orbit. So I have the sun orbited by the Earth, but then the Earth in turn is orbited by the moon, right? And, I have n points. So in fact, you could sort of go, n steps in this process. So that's basically what these iterated Samuelson products of Ptolemaic epicycle story means. It's just these sorts of things. Okay. And I'll just say, again, sort of the key ingredient to the proof is translating to algebra. So the point was the image, come on. Right, so on both sides up top, I have BLMN into this homotopy class of the maps. On both sides, those are just sets. But the point here was, well, in fact, on the right, I end up in a group. And then what we're going to do is we're going to translate the left-hand side also into a group, and then use algebra. And the group is the group of homotopy string links due to Habiger and Lin. And they look kind of like braids, in fact, pure braids. So the blue has to end up right above where it started, and the red and the green. So these are like pure braids, except they're not because they're allowed to be non-monotonic. So this is a perfectly nice two-stranded string link on the right here. And the other difference is they're homotopy, so you're allowed to do link homotopy. So I'm allowed to pass the red through itself. It has to stay away from the blue, but the red through itself is fine. So that's the group. And then the basic idea, well, I care about the map from links to homotopy classes of maps, but back up a step and think about the map from string links over here. And in fact, the image, at least for the Brownian guys, is a group over here. So now I have a map from a group to a group. You have a much better chance of actually understanding what's going on. So you develop some understanding, and then you use that to tell you something about this kappa. And in particular, that kappa is injective, at least on the Brownian links. So that's sort of the basic idea of how the proof goes. And in fact, you can go slightly further. So I should say that you should take this slide with a little bit of a grain of salt. So the theorem I'm about to state is the only theorem that hasn't, been written up and put on the archive and submitted to journals. So you should take it with a little bit of a grain of salt, but we're very confident that it's true. So maybe I'll just state the first part of it. So if I take this class CLM, so what does this mean? So these are homotopy classes of links where there exists a component you can delete to make it fall apart. Remember, Brownian guys, you could pick any component, remove it, and it fell apart. In this story, there is some component you can delete to make it fall apart. So in this case, if you delete the purple guy, what's left is a trivial link, right? But if I delete the green guy, what's left is not a trivial link. So this is in this CLM class, but it's not in the BLM class. So this class is strictly bigger than the Brownian links. So then the theorem with Fred and Rafal is that the restriction of the Koshorka map to this class of links is still injective. And moreover, the image is contained in some group. It's not pi n, but it's tau n. So this is the Fox-Torus homotopy group. So what's missing at this stage is interpreting Milnor invariance of the link in terms of, what's going on in this group over here. But at least we know that you land in this group, and then we're still trying to sort of see if you can actually see the Milnor invariance very explicitly. Okay. And then you can ask, okay, well, what's in the future for us or for anybody, really? Obviously, proving Koshorka's conjecture would be awesome, but actually finding a counterexample would be equally awesome. And I have no real opinion whether it's true or false. Yeah, it would depend on the day. And then, something else. Use these homotopy interpretations of linking invariance to write down integral formulas. So we can do it when n equals 2 or 3, but for higher n, it's very, very much unknown how to do this. And then the hope is that maybe eventually, once you have these geometric integral formulas, maybe you can write down higher helicities by analogy with the, just like the helicity is sort of an analog of the Gauss linking integral. So I think that's all I have. Thanks very much.
That's the Seifert surface for the Borromean rings, is it?
Yeah, so this is a little bit different than the Seifert surface I was talking about because it's just one surface for all three components, but yeah.
Great. Well, yeah.
Excuse me, do you know the old papers in this direction published in physical, maybe?
Well, you mean like your paper
I
and
mean,
like
my
Mitch Berger's
paper,
paper?
and a little bit later paper of Mitch
Berger,
Berger is late.
Mm-hmm.
But in our paper, we exactly consider this question, and not only to 3 links, but to n links, and we write explicit formulas, and all.
Right, in terms of Massey problems.
And what is
right?
important in that paper first,
Mm-hmm.
what I consider this is more original,
Mm-hmm.
that we study not only embedding nodes and links in ordinary space, but to add frame, to add.
Mm-hmm.
So this is what you do, and so what it will be nice to because you consider very complicated generalization of this, but the real formula are just the same.
Mm-hmm.
And we obtain for all, and in for example. Milnor coefficients we apply, and there are only one tune point in this construction that if all previous Milnor coefficients are 0, so this formula are very efficient. If there are some intermediate, there are some, so it will be nice if you compare your, and you know this paper. So it will be interesting what is new, because your machinery is very, it's a little bit more difficult, I guess, that it's necessary to obtain explicit formula.
Right, but the integrals that you, and you can certainly correct me if I'm wrong, but they didn't have this this property of the integrands being isometry invariant, did they?
What?
They didn't have this property where the integrands of the integrals were actually invariant under isometry. So
Yeah. We obtained in the very explicit form, and then in next papers we apply it to the problem of reconnection in magnetic field lines, exactly, and wrote in very explicit. If you not know what this other papers I showed you.
Okay.
I not work in this field for almost 25 years, but what I see that every 5 years the people more or less discover the same formula. Some of them cited, some not.
Yeah.
I don't know if this is a question for Clay or for Misha or for you or someone, but link homotopy means reconnections are allowed or passing through is allowed for some pre-assigned components, and otherwise it's forbidden. I'm just wondering, is there any way that a physical situation has a way of detecting whether these are allowed to cross? I mean, is the ability to cross local phenomenon, or is it one that would actually know which component you're on? So that link
I can
homotopy
answer on your question.
Someone
I
can.
know in some cases the answer is twofold. In some problems it's local, but if you have a serious space of parameter of order, in this case it's not local, because, for example, what we study the following problem, which is if you have twisted two lines in pneumatics, so this configuration will be stable for all times. The forces could not untwist.
Whether it's local or not local, it doesn't seem physical to me.
It depends on physical property.
Well, very much so, but it doesn't seem physical at all to allow one type of crossing and not another.
Oh, well, but I mean, these are also, of course, isotopy invariants. I mean, I'm interpreting this link homotopy invariants just to interpret them as homotopy invariants. But if you're only looking at things with the isotopy, then of course these are still invariants. So you can certainly think of them as isotopy invariants. So the link homotopy is really just a convenience. It's not.
Yeah.
It's not essential to anything.
Any other comment?
Could you comment, why do you think it doesn't extend to vector fields?
Well, so yeah, so if I have my so really these mu bar invariants come with indices like this, and then if I enter, so this is saying I have first component, second component, third component, but then if I say interchange first and second, right, I pick up a minus sign. But of course, in the so by analogy, if I write down the helicity integral, right? If I switch x and y, I don't change the answer, right? Because I pick up a minus sign here, but I also pick up a minus sign here. But in this case, now when I have so this is analogous, if in comparison to the linking integral, right? If I switch the first component and the second component, that's just interchanging these terms. So it's like interchanging these terms. So just switching the order of the points that I pick to do my orbits or whatever. But now for this guy, if this is saying if you switch the order of the first component and the second component, you change the sign. But for a vector field, you're just picking 3 points and letting them go and computing something about the linking of the orbits. It can't possibly matter which order you picked the points, right? So picking up a minus sign is really bad unless it's just.
There's standard tricks with twisted bundles and twisted forms and such.
Yeah. So
Actually, the vector field, it would be some gizmo put on top.
Yeah. So I mean, there's hope that you could sort of make it fancier and get something. But the other thing you could think about is, well, can you write down invariants that have the right symmetries to work as vector field invariants?
Okay, well, a lot of people have tried to find these higher volume integral invariants without success, so this is possibly the reason. Different matter for the line integrals, the analog of the Gauss type integral, as you say. I remember a paper by Sam Edwards way back, and then there was later, I think there was a mistake in that, because I couldn't follow the argument in detail. That always makes me suspicious. And then there was a paper by Rusmaikin. Again, I mean, it's probably as Misha says, they were repeating what you had done in earlier years.
With my search about priority is that our paper was first. Because
When was it? What was the date?
It was maybe it's not a good time to discuss this problem, but it was published in 1984,
84.
beginning.
Yeah, no, this was definitely the
But what is interesting that our paper 1 year was in the journal Communications Medical Physics, because the person who was the reviewer, he asked me to put his name in the reference list because his name was absolutely apparent from this context. I disagreed, and so I got it. So it was some circulation. So
Okay. Probably a long story attached to that one. Well, time for lunch again. Thank you very much, Clay. A very interesting, fascinating.